to the left or to the right one bit so that it doesn't fall into that defective cell. So that is pure and simple. You manufacture more than you need, assuming that there will be some defective memory cells. Very simple. Redundancy. But redundancy comes at the expense of circuit resources. There will be certain circuits, certain device and area that will be probably sitting idle because you are intentionally adding some redundancy. Second approach, which has become an integral part of any memory operation, is error correction. There will be situation when temporary noise and other may weaken the cell, or the cell is defective but it is not defective enough to give you an incorrect result, but it is at the borderline. In that case, we can, even the cell is defective, fully incorrect, we can apply some error correction coding, some techniques at the program level, at the operating system level, to basically address those kind of defect related or yield related issues. So that is called error correction during the runtime. However, in modern memory design, error correction and redundancy both have become kind of standard approach. So in any complex memory design, there will be some redundancy and there will be different types of error correction coding involved to address any defects or faults during the runtime. Yes.
I understand redundancy. What's the redundancy actually means in the memory? Can you explain?
Redundancy means simple. Let's say, let me show you. Let's say you need this many memory slots, this many bits you are storing. So, well, let's say here 10 or 12, whatever. You need 12 memory cell in a row. Instead of 12, you just put 15 of them. If this one you find that this memory cell is defective, then as I am storing the information, that particular bit, instead of storing here, I will store here, so everything else will be right shifted by one bit. But I will still get 256 or 64, whatever number of bits, correct? So I will just not use it.
If it's a defect.
It is defective because before a chip is sent to the user or the assembler who is assembling your cell phone or your laptop, it will go through several layers of testing before packaging and after packaging. So during and then even after this test, full phone is ready and manufactured, before putting it in a nice packet, sending it to the market, it will go through another level of testing, final finished product testing. During this testing, at any phase, if they find out that there is one memory cell is defective, then they will come up with a way to block that memory cell from access and entry. They will use one redundant cell to the left or to the right. That's called redundancy.
I have one more question.
Yes.
Suppose I have an old phone, it has a lot of memory and 8 GB memory, or let's say, over time everything decay, right? So whatever the extra things we have, is it for 5 years, the redundancy is there to make it overcome the usage for the let's say the mobile can last 2 years, but if it stays for 5 years, that redundancy space helps us to elongate.
So but over time, even every cell, due to the aging, there will be defect, it will become slower. So that's why the electronic devices become slower or unreliable with aging. So aging effect, so there is a separate branch of research, it's talk about only aging of electronic device. Because that 2 nanometer silicon dioxide thickness, over the time, thermal expansion and compression will basically change the material property and physical dimension of those transistors, and it will malfunction or it will become slow. So the next issue we have to worry about in any complex memory design is power dissipation. So first of all, we need to know where these power dissipations are coming from. Why we have to worry about power dissipation in memory? It is more serious than logic circuits. Why? Because memory circuits are most densely packed component inside any IC. There are billions of transistors arranged and lines arranged in rows and columns. They are very, very densely packed. So in terms of circuit density, memory component, memory core is the most dense circuitry in the entire computing system. That's why per unit area power consumption and the resulting temperature produced by the power consumption will be very high. That's why if we can save power even by 10%, 5% in any memory core, it will be a huge savings for the overall chip, because 75% of the heat generated in the IC coming from the memory core. So, one of the problem is typically all the memories we actually design at a low voltage swing is reduced with a ratioed design. Ratioed design by default is power consuming design. So on the other hand, mobile devices and handheld devices, any device that is not always connected to power, they need minimum possible power consumption. So, and another very important requirement which is unique to mobile device, like this one, is permanently connected to supply. So you don't care about the leakage or standby power that much, because it is permanently connected. But my cell phone during successive charging, during the standby mode, if it keeps consuming power, I'm losing my battery charge, I have to recharge it quickly. So for this one, standby power, it's just an overall reliability measure. It's not a requirement for it to reliably operate. But for this one, if I'm on a long drive and I forget my charger, which I do frequently, you are in trouble, because standby power must be minimum for this type. So now the question is then, why? What are the sources? If you want to minimize power consumption in memory, you need to know what are the sources in memory core that consumes power. So the most of the power in memory system is dissipated by the memory array by itself, that is the rows and columns where memory cells are organized, and then peripheral devices, that's rows, address decoder, column decoder, block decoder, control circuitry, they will also consume power, but most of the power consumed by the memory core array itself. So the utmost attention should be given to minimize power consumption here. So, and how do we do that? Now at the beginning we have shown the memory architecture. This partitioning of multiple blocks to make each row and column shorter, that is the most effective technique to lower power consumption. Let's say you have a 1 gigabyte RAM, and if you divide them into 10 blocks, you are reading only one memory word at a time. That particular memory word is residing in one of the 10 blocks. So during that particular read or access operation, you do not need to turn on all 10 blocks or all 10 cores. So you only turn on 1 out of 10 cores, so the 90% of the memory system is turned off. So it will not consume any power. But if you design one huge core with 1 gigabyte memory, there is no way of separation. So partitioning complex large memory into smaller core is the most effective way to save power. It gives us, partitioning them into smaller core gives us speedy access, increases the performance, also it saves power significantly. So that's one of the, that's why all the complex large memory by default are divided into smaller cores. And so partitioning the memory to smaller core. The second technique is reducing the voltage level. As we mentioned, we never allow memory cells to be raised from 0 to VDD or lowered from 0 to VDD to ground. We always allow it to change upward and downward a small bit so we can reduce the voltage level, voltage operation. Further, we can reduce the voltage level, higher power savings we will get. So, power operating voltage is a very, very critical factor, and partitioning the memory core into smaller core is also a very, very effective technique. So, final exam will be on December 12th. It's actually 10 to 12 or 10:30 to 12 in. So we will follow UMKC's final schedule. Whatever that final exam schedule given by the university, it is on December 12th. It's either 10 to 12 or 10:30 to 12:30. I will double check.
Will it be in this room?
No, it is something in SCB. I think this is no. I have to double check. I will email you separately later today or tomorrow.
It's Thursday. It's December
It is
12th.
Thursday.
Yeah.
It is Thursday. It is
How
Thursday.
Will it be here?
I will double check the room number. So let me do it right now.
And what about the topic?
What
The topics.
will be lecture 5 to 10? 5 to 10 or 6 to 10?
6 to 10, please.
Okay.
Sorry.
Yeah. So it is 10:30 to 12:30. SCB 209. Is this the one? Yeah.
This room?
209. Okay.
I like this one, lucky charm.
Yeah. So the video recordings are here for part of 7 and 8.
Okay.
So now let's move to our last topic, which is lecture 9.
Question, will you be providing the equation type stuff on the exam, or do we do
If
it
there is
any?
So, from lecture 8, the minimum clock period requirements and the whole time constraint, those equations will not be given. You have to not only remember that, you have to understand that, because that is the part of the understanding. Why positive skew and negative skew, one is subtracted, one is added. Why jitter is always subtracted. So that is part of the understanding, because part of the question will be, if there is a positive skew, how the clock skew, clock period requirements or whole time requirements will change. Do you add it, do you subtract it? So, and then you solve the problem.
But other equations.
But other equation, then I will definitely give that equation in that with that exam. So, in the question. So, this lecture we talk about designing complex circuit block. In earlier lecture we talked about combinational logic circuit. We talked about sequential logic circuit. Using those combinational and sequential logic circuit and other circuit components, we have to design some application blocks within the system. So those application blocks, their job is to perform the computation. And when we talk about computation, what any computers do? it actually implements a set of arithmetic operation. Whether you are doing a graphic operation or you are drawing, you are writing or sending an email, behind the scene, at the lowest level, at the binary level, your microprocessor is actually conducting some arithmetic operations. Arithmetic addition, arithmetic subtraction, multiplication, division, comparison, shifting. These are the things your circuit and system will be actually conducting, no matter what is the application. Fundamentally, it is a bunch of binary arithmetic operations performed by a set of arithmetic circuit and some peripheral. So today in this lecture, we are going to look at first a hierarchical overview of a computing system and how arithmetic circuits are designed. Now, this particular figure, it is showing a hierarchical level of a system design approach. Each of these levels, interestingly, represents a branch in academic, in computer engineering or electronics, microelectronics. Each of these levels also represent a specific career track you will be following in industry or in your research and academic. So the first one at the highest level is the system level planning or system level design. Typically, the device and circuit designers will not be that much involved there. It is more of product development planner with some engineering knowledge. There will be engineers, there will be product developer. This will be a decision made more by the CTO, CFO and CEO of the company with the help of some engineers. That we want to come up with a new 5 gigahertz processors using 10 nanometer technology to beat Samsung or Apple or AMD. Let's say Intel boardroom is making that decision with the input from CTO. So that's the system level planner. It's like UMKC decides to extend its campus eastward or southward or westward. Well, at the new part of the campus, I want 2 dorm building, 5 academic building, 2 lab building, 1 cafeteria building. At the system level planning, right? And then, well, once the system level planning is done, the next level of designer, more engineers, computer architects will come into play, not like device and circuit engineer. They will say, well, within the system, like I said, 5 lab building, 5 academic building, or this, what are the major modules? Logic, CPU block, memory block, control block, how many and in what size and combination? Major modules required to implement that system. The architect. Are we going to use 256 pass, 128-bit pass? Architect, module level design. Under each module, there will be logic gates. How many adder, subtractor, multiplier, AND gate, OR gate, these type of gates we need. Are we going to use all 2 input gates, 4 input gates, or larger gates, right? What type of adder circuit? There are like 1,000 different types of adder technology. Which one we are going to use? That will be logic gate level design, logic level design. Once we decide that, now we have to think about, are we going to design it using 10 nanometer, 5 nanometer, 2 nanometer, or 15 nanometer? Are we going to use ratio CMOS design or regular CMOS design? Or what type of CMOS design? Are we going to use a planar MOSFET technology or FinFET technology or a newer version of FET technology? That's where we're coming here. But the moment we decide that, well, we are going to use an 18 nanometer FinFET, and then device designers, they have to think whether that 18 nanometer FinFET, what material level modification or size and dimension level modification needed to implement the circuit. So in this hierarchical design, where you as the VLSI designer, you are here, but you have to have a very thorough understanding of the device level, or also you have to have an understanding of the logic level, gate level. So VLSI designer can be basically centered here with a significant overlap here and overlap here. So you can say that you start from here, you end here. That is the VLSI designer, circuit designer. Of course, people who are working at the material and the processes of device, there is a separate group. And then below that there is a material scientist, physicist and chemist, who will be talking about the different material, physical, electronic, optical and other properties of material before even getting to the device, right? So that's the whole hierarchical. The entire field of microelectronics or computer engineering starts from here to here or here to here. And even the academic courses are designed at different levels. So now let us look at the major functional block inside any computing system. This is the famous von Neumann computing model, based on which modern digital computing technology is actually has evolved. And this von Neumann computing model digital computing model has 4 functional blocks. The main one is called data path, where computation takes place. It is the computational brain or the core of the computing system, data path, where data is processed, information is processed. And the main supporting block is the memory, where the data and the programs to process those data will be stored. This arrow, bidirectional arrow between them, is that bus, memory bus, or memory wall between memory and the data path. If the number of lanes in this bus, if it is 64, we call it 64-bit architecture. If it is 256, we call it 256-bit architecture. From Windows operating system to every application must be compliant with this one. Otherwise, it will either run slow or it will be only utilizing a small portion of bus at a time. So the architecture here and the memory design here must conform with the bus here. This is the main bottleneck. Now, to have a seamless flow of data and exchange of data and information between data path and memory, so that operation of this one is not interrupted, we have to have a synchronization here. So it is a highly synchronous operation. But the data and information and the instruction to communicate between them must be given externally or collected from a secondary memory, from hard disk or flash or somewhere else. And that will come through your I/O port. But the operation must be coordinated by a bunch of control blocks. And then these 4 functional blocks, internally and externally, must communicate with each other inside and outside. So you need series of hierarchical interconnect network to establish the communication externally and internally, because this data path will be comprised of many thousands of different types of circuits. So internally they must communicate with each other, externally they communicate with other major functional blocks. So you need several types of interconnect network, global, local and intermediate interconnect network. So in general, interconnect networks are divided into 2 types. Global interconnect network, they probably communicate with major functional block or within major block inside a functional block. And the local communication, local interconnects or local lines, they communicate from one gate to the next gate to the next gate, local communication. It's like the internal road inside the campus versus the Highway 71 connecting like 2 different states, right? So these are the major functional blocks within von Neumann computing architecture or current modern computer. So the computational block, today we already talked about what goes inside memory. It can be ROM, it can be RAM, or it can be cache memory. We already talked about that. And control circuit is just a general control circuitry. I/O is our input or iPad or our touch screen, or it can be a flash drive anywhere. But computer engineering mainly evolves here and here. So let us talk about what we have. It is made of circuitry for mainly performing computation, because that's where computation takes place. And there will be some supporting block other than arithmetic circuits to perform the computation. So what type of computational circuitry we are talking about? There can be computational logics to make the decision and computational circuits to make the computation, mainly arithmetic operators. Those are adders, multipliers, shifters, comparators, subtractor, dividers, many. Interestingly, it is observed that, so there will be some register also inside the data part. What is register? Register is temporary memory block. Because when you are performing, let's say, an addition operation, you are adding 4 or 5 numbers. You fetch entire set of numbers from main memory inside the data part. You don't want to go back again and again back to the memory. You want to just hold it in the register and then do the addition. So a data path will be comprised of a bunch of registers, and we know how to do registers, how design an operation in previous lecture. Adder, subtractor, multiplexer, and different circuitry. Now, in this hypothetical diagram, why we just add adder? Earlier we mentioned that we need subtractor, we need multiplier, we need divider, we need comparator. Interestingly, every single arithmetic operation in binary algebra is nothing but a modified form of addition with the help of some logic operation. So basically, entire computation is nothing but a bunch of binary addition. So subtractor is nothing but different types of adder. A multiplier is nothing but a combination of some logic circuit and adder. A comparator is also a bunch of logic circuit with an adder. So, summary is, entire data path is the computational core of the computers, and the core of the data path where computation will take place mainly is a bunch of adder. So, whenever people are trying to improve the efficiency and the computational capacity of CPU, they're mainly talking about increasing the efficiency and the capacity of the adders. So, majority of this lecture will focus on adders. So we all know that binary addition, just quick recap. If you want 0, 0, 0, 1, 1, 0, you get only the sum bit. But if you add 1 plus 1, you get a sum bit and you get a carry bit. So, while you are doing an operation, you do not have, let's say, one binary bit addition with another single binary bit. It can be any of these 4 combinations. But for this combination, at the output, if you make it a single bit output, you can only take care of these three combinations. Your output, in this case, must have 2 output bits, so that you have 1 slot for sum bit, 1 slot for carry bit. This is a simple binary bit by bit addition, and it will need 2 output bits, 1 for the sum bit, 1 for the carry bit. Like if in regular decimal addition, if you add 7 with 6, 7 plus 6, 13, on the sum bit you write 3, there is a carry you write 1. That carry and the sum bit 1 and 3 makes 13, 6, 7 plus 6. Same thing for the binary, we need a carry bit. So minimum for 1 bit binary addition with another 1 bit binary, we need minimum 2 output bits. So, and that is called a half adder. 1 bit binary, so the first column is the sum bit, the second column is third bit. Now this is the truth table for a half adder. Now, if we look at this truth table, as you can see, x and y are the variable inputs, 2 inputs. For this output bit, the sum column acts like an XOR operation of input x and y. This carry column acts like an AND operation of X and Y. So the implementation of where this black thing is coming from, I don't know. This implementation of this half adder is from X and Y. If I got an XOR gate, I get the sum bit. If I get an AND gate, I get the carry bit. Right? This is just an illustration how we do actual hand calculation. If I have 1 bit by 1 bit, if I add this with this, it will create a sum bit, but very likelihood in 50% case, it will create a carry that must be added to the next column. That's what I do, right? If we add a big number with another big number, we start with the leftmost. Add them. If there is a, put the sum. If there is a carry, we send it to the next column. Add them. If there is a carry, we send it to the next column. So the carry out for this column becomes carry in for the next one. We add, we send it next, and then we have a final carry. We put it here, then we get the whole result. That means if we think about each column, we always have to accommodate for the maximum need. Like in the half adder, we cannot ignore that. That's why we have to add these two output, right? In the 1, 2, 3 carry is always 0, we could design the circuit without this option. But we have to worry that X and Y can be 1 and 1, so we have to have a second output slot bit ready. Similarly here, at any column-wise addition, how many maximum bit each column must handle? 3. 2 of the inputs plus a potential carry from the previous column. Yes, first one will not have something, but every subsequent one may have 3 bits to be added. So the column-wise addition will look like this. An input A, input B, and a carry in coming from the previous column. So, but half adder, the way it is designed, it can only take 2 input. But this one is saying that every column will have maximum 3 input. 2 of its own input, and the previous column is sending another input in the form of carry in. So an actual adder circuit, bit by bit adder circuit, even you are adding single bit at a time, must have 3 options for 3 inputs. With the half adder, we proved that we need minimum 2 output bits. Now, with the complex number example, we have proven that for input we need minimum 3 inputs. So, a binary bit by bit addition circuitry, let's put in a box, must have 3 input terminal and must have 2 output terminal. This 3 input terminal will be X input, Y input, or A input, B input, whatever, carry input. And output will be sum and carry out. It will be then carry in, right? So at any binary bit by bit adder will be a 3 to 2 binary circuit, 3 input, 2 output. And that is called a full adder. An adder circuit which can take into consideration the possibility of having a carry in. This is just a quick recap. A full adder circuitry, the equation for sum bit and the carry bit is given by this equation, and we can implement this equation with this circuit. So if you look at inside a full adder, and if you compare it with the half adder circuit, you can see that a full adder is nothing but a combination of 2 half adder with an OR gate. So this is the logical implementation of a full adder circuit, right? So what this full adder can take care of? It can take care of 1 column addition at a time. So if, let's say, if this is the first column, so the 0th column, in binary it starts from 0, first, second, third, and fourth, right? If the 0th column, in this case this one will be 0, carry in is 0. But for all subsequent one, Zeroth column may send the carry to the first column may send the carry to the second column may send the carry to the third column, onward, like regular decimal addition we do. So now, if we have a complex multi-bit binary number, addition will take place in multiple columns. So let's say we want to put this whole circuitry inside a rectangular box. And we want to construct a multi-bit binary adder. Let's say we want to construct a 4-bit binary adder. 4-bit binary number, 3-bit binary number. So there will be 4 column-wise addition, and then there will be a final carry out on the 5th position, right? So inside this box, I will have this full adder. It will have a first carry, right? Carry of the 0th column, which will by default 0. Its input, it will create a carry in. This carry in and its own input will be added. It will create a carry 2, but it will also create its own sum bit. This carry 2 will be added to the second column. It will create sum bit 2 and carry for 3. Then sum bit 3 and the final carry 4. Final result will be carry 4, S3, S2, S1, S0. This will be my final result.
And
but how we are constructing multiple bit binary adder? This is a single bit full adder. We are just connecting them in the exact order the way regular addition is taking place. We are adding first 0th column, generating a carry, sending it to the second, sending it to the third, fourth, and onward, right? And this type of complex addition adder design is called ripple carry adder. The carry bit is rippling through the chain of adder from the rightmost column to the leftmost column. So we are following exactly, the construction follows exactly the way we calculate by hand, right? So let's say we are adding a binary number 10011 with another binary number 1101, right? So this is 0th column, first column, second and third column. We first add these two, write sum bit here, we send carry here, write sum bit 2, and then we send carry here, write sum bit 3, we can carry sum bit 3, and then we have a carry 4, right? So we are first conducting this operation, sending it to the left. Same thing, we put an adder here, left, 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 so it is the carry is moving from here to here, here to here. So this is the simplest possible straightforward design of complex adder. If we know how to design a full adder from its equation, we will just, if I need a 64-bit adder, I will connect them, 64 of them in series. From left to right, it will ripple through the chain. That's why it is called ripple carry adder. So, the time for this adder to generate, because you as a computer designer, computer engineer, you need to worry how much time and circuit resource I need to generate the addition. So let's say you are talking about 64-bit architecture, and you may need a 64-bit binary adder to compare or add two numbers. So I have to connect 64 of them in series. So can this last adder generate its result before getting this one? No. Can this one generate its result before this one? So it's a serial operation. This one must wait this one to generate C1. This one must wait for this one to generate C2. This one must wait for generate to C3, right? And so on. And final C4 is not ready until all of them finishes their job. So, but while C1, C2, the carries are traveling forward, these bits are already ready, right? So you don't have to add time for generating sum 1 to time for the sum 2 to 3 and 4, right? As carry is traveling forward, these bits are already available, right? So that's why the timing, the delay of generating final result will be in the order of n being the number of bits we are adding. If we are adding 64 bit, there will be 64 bit adders, the delay will be in the order of 64. If we are adding 8 bit, there will be 8 adders in the order of 8. But let us look into further detail. Yes.
But the S0 and S0 is created after the A0 and B0, right?
Yeah.
But the S1 needs to wait to get the response of C1, then
Yeah.
A1 and B1.
Yeah.
So there is also delay for
So
the
no.
output.
C1 is generated. By the time C2 is ready, so I am adding. So what is the time to reach here? Because this one cannot start without this one is available. This one is available after the time needed to generate C1 plus the time to generate C2. C2 is available. The moment C2 is available, this 2 is already available because you know what two numbers you are adding. You already fetched those numbers from memory. So this one can start its operation. But by the time C2 is available, S1 is already there. So then you don't have to add C1 plus C2 time plus C2 plus time S1. Because by the time carry C2 is available, S1 is already there. So you don't have to add time for C1 plus time for C2 plus time for S1. Because C2 and S1, they're simultaneously ready. So you don't have to add that. But you have to add first one. Because first one I didn't get anything. I have to wait for this one and this one to be arrive. So 1t sum and then how much time it took. This is ready. Now, as you can see now, total error time is n minus 1t carry plus 1t sum. So I only added the first one.
1t sum.
Yeah. And then I multiplied t carry. T carry is the time to generate carry by n minus 1 because by the time C3 is ready, reach here, these two are simultaneously available. So I don't have to double count this one or double count this one. So that's why it is n minus 1 times t carry plus 1t sum. By the time this one is ready, this is already there, right? So 1, 2, 3 t carry plus 1t sum. Because these two are available almost simultaneously. So the delay of this error circuit is n minus 1 times t carry plus t sum. So what is the, so very simple. But the problem with this, each of these rectangular box will contain this circuit made of 1, 2, 3, 4, 5 logic gates. When I say 5 logic gates, it's actually not 5 logic gates because we don't get AND directly. It is actually a NAND followed by an inverter. We don't get OR directly. It's actually a NOR followed by an inverter. So inside this full adder, there are lots of different transistors and logic gates needed. So if we try to implement this circuit as it is, what do we get? We get, I believe we need 36 transistors just to implement one full bit adder, which can add only one binary bit with another binary bit with the potential of having a additional carry. Just for one binary bit column addition, just for one column addition, I need a full adder that contains 36 transistors. And it's a serial operation, yes.
It will, I don't know, it's stupid question or not.
Yes.
The if adding for addition we need 36 transistor. How many transistor are there in a processor that it processes so many things at a time?
That's why the transistor numbers are in hundreds of millions, in billions right now.
Yeah.
So that's why you need actually the data path needs so many. Good thing is this type of complex adders you don't need that many. Probably you need several sets. Same adder circuits are being used repeatedly. So, but yes, that's why designers, they pay tremendous amount of attention to reduce this number. If you can reduce this number even by 5%, from 28, bring it down to 36 to 32, 30, that is a huge savings. Because when you are talking about number of transistors in millions. So, what is the most critical design path or signal path you have to target as a designer in this ripple carry error? It is the carry generation path. Because in the worst case, every column may have a carry in from the previous column. In some case, let's say in a decimal, in a column, you are adding 2 with 3. Result is 5. It will not generate a carry in for the next one. So next one can just add, let's say next one is 7 and 1, it can just add 7 and 1, 8. It doesn't have to worry about a carry coming from the previous column because previous column was 2 and 3, right? So in binary, you will have a carry for the next column only when if the inputs are 1 and 1. So in the worst case, if these are 1 and 1, 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 this cannot do anything until this one is generated. This cannot do until this one is generated. This cannot do this until this one is generated. There is entire operation depends on how much time it takes for this carry to propagate all the way to the last one. So if I can, so I have to always design for the worst case. So if I can minimize the delay of the carry generation and propagation from the first bit to the last bit, then I can improve the design. Just look at this equation. This tells you if it is an 8-bit number addition, it will be 7 times T carry plus 1 T sum. So you as the designer, would you focus on reducing T carry or T sum? Definitely T carry. If you can minimize the time to generate each carry bit just by 1 picosecond, you will be getting 7 times 1, 7 picosecond saving. But if you can reduce the time to generate some bit by 1 picosecond, you are getting only 1 picosecond saving. Because the weightage factor here is much higher. So that's why this carry generation path and propagation path is considered the most critical path or the most critical design target for the designer. So now and then inside each rectangle we need 36 transistors if we want to implement this circuit as it is without modification. So now people started looking at different ways to improve the design. One of them is logic level manipulation. So the entire computer engineering regarding data path, the number one target is to optimize and maximize the design and efficiency of adders. There are logic level manipulation, there are circuit level manipulation, or there are architecture level manipulation to improve the error design. Logic level manipulation targets simplifying this equation or finding some common factors in this equation which can be exploited to minimize the complexity. So we are going to see one such logic level manipulation. Let us first look at the truth table of a full adder. A full adder is a 3 input, 2 output circuitry. We summarize that. 2 inputs are input A and input B, and 1 potential carry input, and outputs are sum bit and carry output bits. Forget about this column. Now, in a 3 input circuitry, input combinations can be 8 different types, right? From 000 to 111, 2 to the power 3, right? It's a 3 input binary combination. So the total combination will be 2 to the power 3, 8 different input combination from all zeros to all ones. Now for all these 8 input combinations, 3 inputs, 2 input bits and 1 carry bits, what are the results? Using the original equation, I can see that this will be the result for the sum output, this will be the result for the carry output. Now, let us utilize our observation power. What is actually happening in the sum column and the carry column for all possible input combination? As you can see, in the first 2 rows, inputs are 0, 0. In one case, and carry can have 2 possibilities. Sometimes carry can be from previous column, I can inherit a 0 carry or I inherit a 1 carry. So for those possibility, carry out will be, as you can see, 0, 0. So what is the conclusion? If the inputs are 0 and 0, no matter what is the carry in from the previous column, my carry out will be still 0, 0. That is, and then the second possibility. If the inputs are 0, 1 or 1, 0, let's this pair 0, 1, 0, 1, and I will have 2 possibilities for the carry in. What I am looking at the carry out column. If inputs are 0, 1, it is also, if carry is 0, in is 0, carry out is 0. If carry is 1, carry out is 1. Same thing for 1, 0 input combination. If carry in is 0, carry out will be 0. If carry in is 1, carry out is 1. Because if one of the input is 1 and then we add it to carry in 1, definitely it will generate a carry out, right? So, middle 4 rows for 0, 0, 0, 1 and 1, 0 input combinations, carry out will exactly be the carbon copy of the carry in. If carry in is 0, carry out will be 1. Carry out will be 0. If carry in is 1, carry out will be 1. So, and we are defining it as propagate. That means on the input side, we are talking about 2 original inputs. If the original inputs are 0, 1 or 1, 0, before column 2, let's say we are talking about column 2. Column 2 is adding 0, 1 or 1, 0. And from this truth table, we know that if the input combinations are 0, 1 or 1, 0, carry in and carry out will be the same. So that before column 2 finishes its job, I already know what will be its carry out the moment I saw the input. And I saw the input at the beginning, right? So the column 3 can start its job without waiting for column 2 to finish its job, because I already know, no matter what is happening previously, what will be the output for carry 2, which is carry in for column 3, right? So I am using my observation to basically make a decision ahead of time, so that column 3, if this input combination appears in any column, the next column can start its job, because I already know what will be the carry coming in from the previous column, right? So that is called propagate. Now, first two, if the first two row inputs are 0 and 0, no matter what is the carry, 1 or 0, that column will not generate a carry out, because two inputs are 0. Even if carry is 1, 0 plus 1 is 1, it will not generate a carry out. So I am calling it delete. That means if column 2 inputs are 0 and 0, we already know that it will not generate and carry out. So column 3 can start its addition without waiting for column 2 to finish its job, because we already know column 3 will be getting a 0 carry out, carry in, right? So that is, we are calling it delete. That means if column 2 is getting 0, 0 input, delete everything from column 3 carry in input, it just put a 0, right? That is, so that is we are making decision ahead of time for the subsequent column. Now, if the inputs, last two row, if the inputs are 1 and 1, irrespective of what you have in carry in from previous column, it will definitely generate a carry out. If the carry in is 1, then it will have a sum bit 1, carry bit 1. If carry is 0, it will have a sum bit 0, carry 1. Right? So, and we are defining it as generate. That means if you see that in any column, inputs are 1 and 1, you automatically know for that column carry out and for next column carry in will be 1 automatically. So we are making the decision. So we are converting our serial operation to somewhat parallel operation. We are making decision ahead of time. If we can do it for at least 10 out of 64 columns, then this number will be, and the normal, it will be normal carry, ripple carry error, it will be 64 minus 1, 63 carry. But for 10 column, if we can make the decision ahead of time, it will be then 53 minus t carry, right? Because we already know for at least 10 columns. So that is the benefit of utilizing the observation from the truth table. So this delete, in some literature it is called kill, propagate and generate. These are defined as 3 intermediate signals in adult circuits. So if A and B both are 0 and 1 and 1, generate will be 1. No matter what, if A and B are 1, there will be a carry 1, we call it generate will be 1. Propagate, if A or B 1, then we will just follow, we will just transfer, we will assume that carry in and carry out are same. We are propagating carry in to the carry out. So, and that is A or B, because it's 0, 1 or 1, 0. So if propagate signal value is 1, then we know that carry will propagate, same carry will propagate. If A and B both are 0, then delete or kill signal will be equal to 1, then we know that the next carry will be automatically 0. So now you know what two numbers you are adding. So you know A's and B's. A10, A0, 1, 2, 3, these are the bits of the number A. Similarly, B0, B1, B2, all this, these are bits of number B. You know what two numbers you are adding, so you already know all the A bits and B bits. And generate, propagate, and delete or kill intermediate signals are dependent on the inputs you are applying. So the moment you know the inputs you are adding, the next step, you can test for each column, is it a generate, is it a propagate, or is it a delete? From the input bits itself. Here, we don't have to wait for the full addition. So once we know this, then we can basically skip or assume certain column what would be the carry. Now, using this intermediate variable, we can reorganize the sum bit equation and the carry bit equation. First, here I am showing you an alternative expression of carry and sum. So here, this equation was a direct implementation of the circuit itself without any logic level manipulation. But from our previous lecture, we know that before implementation, we have to expand this equation and do all sorts of logic level manipulation to simplify the circuit. And it is observed that some bit we can also simplify by expanding those XOR. Also we can simplify the carry bit. I did not show all the steps, but this is an alternative expression for sum bit and carry bit with some manipulation. Now we can also express this equation in terms of these intermediate signals, A B equal generate, A or B equal propagate, A bar and B bar equal to delete or kill. And if we express this sum bit expression and carry bit expression in terms of this intermediate variable as defined from this truth table, carry out will be a function of generate plus P time carry in. Sum bit will be propagate with XOR with or with CI carry in. So what is the benefit of expressing the carry out and sum bit in terms of intermediate variable? Because for every column you can generate this signal, generate for ith column, propagate for ith column, delete for ith column as soon as the inputs are known, and then plug them into this equation. So you can generate carry out for ith column, sum for ith column from those intermediate signals. You cannot do it for every column, but you can do it for majority of the column if it falls into any of those observations. So that will expedite the operation because the equations are now much simpler. Here generate is nothing but A and B, propagate is nothing but A or B, kill or delete is nothing but A bar and B bar, right? So that actually saves our time. In some literature it will say D, in some literature it will say K or kill. So these are done by logic level manipulation. We have just played with the logic function, simplified it, and then you looked at our truth table and used the observation to come up with a simpler logic function. So that is a huge savings. So now this simpler function, these two simpler functions we expressed here, we can further modify it. We can further modify it and come up with this even simpler expression. Now if we implement that into logic circuit, this is the logic level implementation showing all the gates, and if we convert this logic level circuit into transistor level circuit, this is what we get. Of course, I didn't show the simplification step, and this implementation is what? 28 transistor. So without any modification of the equation when we implemented that one directly, we needed 36 transistors. After 2 levels of logic simplification, we could implement it with 28 transistors per one full bit adder, and that is a huge, but still it has some problem. It has very large load capacitance for carry out, because carry out is generated here So it will see all the series transistor here. As you increase the number of input, this one will grow, right? So the as we said, still carry generation is the main thing. We don't care about sum bit because this time is embedded inside the overall delay, but this one is serial delay, so we have to simplify further. So in the next class, we will see more additional techniques for circuit level manipulation for adder circuit. So later tonight or earlier tomorrow morning, you will get an email with the assignment or take-home quiz for lecture 10, as well as lecture 7 and 8.